Okay, so don't know why it shows 4, 6. There are a lot of things to write down, but we'll go with it. Okay? If it reduces to this form, then what's its rank? Okay? Rank is 3, but I'm going to write that last. What else is the rank? It's the dimension of the row space. You've got to know that. Okay? That's going to be really important, and increasingly so as the course goes on. It means if you write down the rows of the matrix A, there are 4 of them, right? Write those rows down as a set of vectors. And then figure out what the dimension is. Are those vectors going to be linearly independent? How many of them are there? Huh? The original A matrix, how many rows does it have? I can't hear a word. There must be some kind of resonance in this hall or something. People across the hall always sound really loud. Okay, what's... Okay.
4 rows.
4 rows. Okay? And the rank is equal to the dimension of the row space, right? And what's the dimension? It's number of linearly independent row vectors, isn't it? Okay? In this case, number of linearly independent row vectors is less than the number of row vectors. Because in this case, the rank is less than 3. Now, you know, if we had a 1 here, then maybe an asterisk here, because that generally follow, then your rank would be 4, and all your rows would be linearly independent. Okay? Now when we get into linear transformations, that tells you about the dimension of the subspace you get when you're mapping this thing. Okay? Now we won't worry about that right now, but think back to what we did earlier about the pictures of lines and planes and so forth, and those as subspaces of R2 and R3, right? Okay? Because you want to keep that intuition, because you're going to need it. Within 2 weeks, you're going to need it very badly. You're going to wish you had it if you don't. Okay. So there we have that. Okay, well, we can kind of stop there. I could say a lot more, and will. But in this case, that would be 3. Okay? So, what's the nullity?
Number of 0 vectors.
Get your number of 0 rows. Okay? Okay? And what else is it? Well, it's M minus rank, where M generally stands for what? Number of rows, right? implicitly, I'm referring to the number of rows because generally the matrix is an m by n. That's our general way of referring to the dimensions of a matrix, okay? So I could have written number of rows minus rank, okay? But of course, the rank is the number of rows that aren't 0, so that's pretty obvious, right? Oh boy, think about the words you're going to write. It's a number of rows. And that should be obvious, right? Because your rank is the number of non-zero rows, you subtract that from the number of rows, you got the number of 0 rows. Okay? That is equal to the number of vectors in whatever space you have that map to the 0 vector. Okay? And I'm going to change my wording a little bit. Instead of vectors, I'm going to say column vectors. Okay? Because I'm thinking in terms of linear transformations, and we haven't talked that much about them, and the language I just used is more appropriate to that. Okay? Now, a set of columns in what space? What kind of columns get multiplied by this matrix?
4.
Sorry?
You'd have to have 4 columns to multiply it by that matrix.
No, you just have to have one column. In other words, if I put something over here, how many numbers would I have to have?
6.
Sorry?
6.
Can't hear.
6.
Yeah, hold up 6 fingers in one hand. Okay. Yeah, you can't do that with one hand. Okay. Right? See this, one hand, 2 hands, 4, 6. Never mind. And that, never mind that either. Okay. Dimension of the set of columns in and let's call them columns X in R6. That map to 0. That's what the nullity is. Okay? It's the dimension of the set of vectors that this thing maps to 0. Okay? So, it's a very important picture, essential for understanding the things you need to understand about vector spaces, and essential in numerous applications.